So Yimin Zhong from Auburn University, and so Yimin got his PhD from UT Austin in 2017. He spent a few years in UC Auburn and also Duke University for postdocs before he joined Auburn in 2022. He's gonna talk about how much can one learn a PDE from its solution. Thanks, Yimin.
Thanks for the introduction. So if you look at the title, so it's kind of like okay, this is just a question. So how do we learn this PDE from the solution? So to introduce that, we first okay. So first we try to bring up the concept about what is the PDE learning. So what does this thing do? So the background is that we already know that PDE models are very useful everywhere. So you can see the PDE models in all kinds of areas. And the reason about that is that it has a very effective and concept representation to represent the underlying physics. And also, if you use a PDE model, usually the coefficients are already interpretable. You will know the physical meaning for each of them. And it helps us to understand the dynamics, try to predict the sequential, the subsequent behavior of the dynamics. And of course, you can also use that to design faster, efficient algorithm to solve these issues. But the limitation is also very clear, is that the PDE models are often oversimplified, and many kind of relation are built on the heuristic laws, like the power laws for the attenuation. So so then we will have the question that suppose we are able to observe some kind of a solution or part of the solution data from an underlying PDE. Can we try to find out what the more sophisticated PDE model to represent that physics? And to answer this question, we will have the following questions as well. So first is what is a suitable parameterization for PDE model? So so what kind of framework are we looking at? And if we want to learn the PDEs from the solution data, how much data do we need, right? And if the learning is possible, then what is the computational cost?
How are you?
And after that, you can do the error analysis, etc., etc. So we're not trying to work on the PDE model for every model. So we focus on a very common one, that is the evolution model. And the evolution model actually has been seen in the Hilly equation, convection transport equation. This kind of very well-known models. And here we only look at the very simplified settings. That is, the domain is actually periodic. And we have the initial condition F, we have some operator L that is representing the underlying PDE, and on the left-hand side is the time derivative. And to represent the PDE model, we only try to bring up some the linear modeling. So let's say, so we got the linear combination of the derivatives, and the coefficients are some smooth coefficients. And with the highest degree here, we assume is capital N. And in this framework, we try to learn these PDE coefficients, P alpha, from the solution data observed from a span of the time domain from tau to capital T. And it turns out that this is not a very new thing. Actually, there are many works already on this kind of stuff. And typical approaches that can be divided into two categories. The first, we call that approximation of operator. But basically, we try to learn this operator L instead of learning the underlying PDE. And the idea is that you treat the inputs at time t, you treat the inputs of the solution at time t, and you connect the outputs at one step further. And the matrix or the operator in between, that is the propagator. And basically, if you have the inputs and outputs, and as long as you can connect many of them, you can always fit the operator in between. And using this kind of approach, basically, you solve the linear equations, and it's very flexible. And the downside is also very obvious. That is, you have to pay the expensive computational cost to invert the matrix. And another downside is that after you reconstruct the propagator, it's hard to interpret what is the really inside. You only know that it's mapping from some input to an output, but you don't know how to interpret the coefficient in this big matrix, for instance. And the second category of the approach is called the identification of operator. And in this kind of approach, the usual setting is that we have a dictionary of operators. So here denoted by this phi beta. Beta is the subscript. And given this kind of a dictionary, and the problem turns out to be, can we find out what kind of operator in this dictionary are in this operator L? Instead of reconstructing the detailed coefficients, here we only want to know what kind of terms are really inside, instead of finding a very precise interpretation of this operator. And for this kind of problem, usually it's relatively cheap. And but the problem is that if you want to do a very good reconstruction, you need a very nice prior information about dictionary. So you need to know what kind of physics you are looking at. If you are say there is a underlying physics that has some diffusion and you miss that, then you probably get a totally wrong physics. So this is the issue. And regarding the existing works, so here is just try to give you some a little bit of references. That is maybe some the list is far from complete. So here just list the idea. So for the approximation, the typical approaches are basically in the can be seen from these two papers. The one is the Dongbing from PKU and the Dachen Xiu from OSU. They have done this kind of work. Basically, you're trying to reconstruct the matrix, the propagator in between as matrices, and from Dongbing's work, it's basically represent that operator identity plus this delta t times the differential operator as a network, and try to find out the structure of network and interpret it. And for identification, they're actually also very there's a lot of work for this under this thread as well. And the typical examples are like the Bruton from the University of Washington and Songha from Georgia. They have done many works on this. So try to identify what kind of operators is inside this underlying physics. Okay, so we try to distinguish our work from theirs. So what is their issues? So in all of their works, they assume that the availability as many as they can. So basically, they assume that you can have access to all solution, density in time and density in space. So and also you can have access to diverse initial condition. Basically, you can sample initial condition sufficient many times, and you can collect all the solution trajectory, and then you will collect a lot of data and try to do the reconstruction. And that is not very physical as from our view. So for instance, suppose you want to study a recessive system, and if you manually perturb the initial condition, you can also possibly perturb the system. So you're not looking at the same system as that. Right. So we're trying to look at the single data trajectory. So basically, you have only one initial condition, and instead of dense sensors or dense observation in space and time, here we also assume that we only have the local sensors. So basically, we assume that the data can be only accessed from some patches. So only a small open set in space and time. Then that's the place that you can observe. And also, there are some possibly time delay. So when you place the sensor, and you will have to wait for a few, maybe milliseconds then you start to give readings. So this is just some very practical assumptions. So we try to bring up this single solution trajectories theory about this problem. And under this kind of topic, we want to answer this following question. So how much data is available in a single solution trajectory? So because we want to use a single trajectory to do the reconstruction. And we also wonder if it's enough to do this thing, and if we have only local sensors, is that possible to find a robust way to learn this PDE? So these are the three fundamental questions we want to ask. And it turns out that to give a very precise answer to this question actually is really, really difficult. So we start from something that is more or less typical. So the toy model is a parabolic type. So basically, if the operator L, that is an operator we want to learn, is a strongly elliptic. So basically, a very in general, like a second order strongly elliptic operator that's a strongly elliptic. And then you will have the downforward integral form for the solution operator. And basically, that the solution operator can be represented as a contour integral that wrapping around this spectrum. And then then you can see that if I can evaluate this contour integral precisely, I can recover this solution operator. And it turns out that this actually can be reduced as a problem that finding a very small set of quadrature points to represent this contour integral. And you can see that when the time variable is between two numbers and this initial time is can be very small but not zero, then you can discretize this integral operator into a finite dimensional one, and the total number of the quadrature points is only proportional to the polylog of epsilon. So which means that you only need a very small number of quadrature points to represent this integral well, which means that this solution operator actually in terms of epsilon to rank actually is very low. So if you allow some threshold epsilon, then you can use a low dimensional operator to approximate this solution operator, as long as your time is not at zero. So this gives us some very quick corollary that is if the initial condition or near the initial condition, the solution also span a very low dimensional space, then you combine this initial times low dimensional space and the later time low dimensional space, then the whole solution's trajectory will sit very close to a low dimensional space. And indeed, if you allow this, if you assume this operator permits some a complete set of eigenfunctions, then assuming this initial condition has certain kind of decay in the coefficient, then you can show that you can find a polylog epsilon dimensional space. When you map the solution into that space, the error is very small. So if you say, then that means that if you allow there's enough noise in the gradients in the solution, then the intrinsic dimension in the solution space actually is very low. It's just like polylog of this noise level. Okay, then in contrast from the parabolic case, if we look at the hyperbolic equation, actually the case will be very different. So to see why is that different, so we just take a first order transport down torus as example, but the general case are very similar. Then it turns out that your dimension actually only rely on the regularity. So for the above case, the transport case, then if the coefficients and the initial condition they're sitting in certain regularity class, then you can show that the solution generates a subspace of the dimension that is in terms of epsilon to certain power, and this power rely on the regularity. When the regularity p goes to infinity, you can see this dimension could be very low. However, if the coefficients here are having some kind of discontinuity or having some bad regularity, then you can imagine that this kind of transport equation is basically propagating the singularity. So you have certain singularity there, and the transport equation can propagate that. And as long as this propagation can continue without any attenuation, then you can also track the singularity to get this the underlying physics without any issue. So you can see there are these two examples actually give you the fundamental difference in one regime that you cannot hope to get a very good characterization of the solution in terms of dimension. In another regime that it only relies on the regularity. And indeed, if you we showed some toy cases. So here we illustrate two graphs in terms of the sample solution matrix. So basically, we sample the solution to a transport equation and a parabolic equation, and we sample the solution at the uniform in time and uniform in space, and we stack the solution together as a matrix, and we try to find out the solution matrix singular value. You can see for hyperbolic case, we ended the log plot. You get a straight line. Basically means that you get the singular value is certain kind of growth decays like the certain decays as the index to some power. And in parabolic case, if you use semi-log, you get a straight line, means that it's just a log factor. So it's a perfect match to the previous results. So how does this help us to understand the previous PDE learning? So intuitively, if we have some coefficient in the operator L that we want to recover, then if we want to do the reconstruction, you have to discretize, for instance, numerically. Then the problem will be very difficult if the discretized parameter space is much larger than the solution space. Basically, that means that you don't have enough dimension to span that match parameter space, right? Basically, it means that if you have a very small space of a solution and you have a very large parameter space, then if you construct this mapping from a low dimension to high dimension, you have to this kind of mapping you have to be very opposed. So that will make the problem very difficult. But for hyperbolic case, this kind of thing could be a little bit better because you have the regularity to help. But for parabolic case, possibly you don't have sufficient data. So in terms of so here we just use the alignment to show this like the parameter space. It's the probability is very large, but as a solution space, it just squeeze all the information away. And if you want to construct this the inverse mapping here, it would be very difficult. Okay, so we say that it's very difficult, but we still have some question here. So in the previous works, as I mentioned, the many works have already done this kind of problem with many initial conditions. So can many initial conditions help in this region? So in terms of if we have a lot of solution space, all squeeze information away, does that sum together better than a particular one? So this is something that we want to understand. If this is not true, then that means having more initial condition does not help you, right? Just one initial condition could be just what you have. So in this kind of case, here we have some footnote here. That is for the initial condition, we want this initial condition have some first possible time delay. If not in that case, then you think about it, you have initial condition included, then you can span the initial condition in L2 space. You resolve that space very well. Basically, you choose order Fourier space, you can resolve that space very well. Then there's no issue here. So we have to exclude that case. So we have to include some possible time delay. So for all the initial condition, we think there's some time delay there. And can we say the trajectory of that many delayed solution span a larger space or not? So to answer that question, we try not to make things too complicated. So we start with some self-adjoint elliptical operator L. And the dimension, of course, is even here. And we wonder the following. Suppose we have one particular solution U. That is the very special one. And for any other trajectory solution W, and can we find a weight function that is new depending on the T and this tau? And belongs to L2 space. Basically, it's used. This requirement is placed here just for computation purpose. That the arbitrary solution can be represented as a linear combination of the particular solution. So it's represented as an integral. So basically, if you can find the weight function nu here, and you combine with your particular solution U, and you take the integral. If you can use this kind of form to represent any solution, that means no matter what kind of solution W you choose, one solution U is enough, right? Because the solution space spanned by U that can represent anything else. So to answer this question here, we just use the self-adjoint operators property. We use the eigenfunction to write down all the solutions. So U is expanded by eigenfunctions. W is expanded by the same set of eigenfunction with different initial conditions. So Cn and Fn basically is the coefficient for initial conditions. And we want to find a wave function satisfy the following moment problem. This is similar to a Hamburger moment problem, but here is the more specific. So that is the integral from 0 to t, that is the exponential function multiplied this wave function equals a particular number. That is related to the initial conditions ratio of the particular solution and the arbitrary solution. So if we can find the wave function nu satisfy this moment problem, then that means the previous result actually is true. One solution can span any other solution if the other solution has some time delay. And to answer this question, we need these two assumptions. The first assumption is that there's some growing condition of this eigenvalues, and this actually is a very natural thing if you study with the elliptic operator. So basically, this beta will be the order of dimension, if you are familiar with Weyer's law. And this small n of n to the negative sigma usually is true if the coefficient has some certain regularity. So this actually, the first assumption actually there is very universal for general operators. The non-typical assumption is the second one. That is, we need some small gap, at least some small gap between these eigenvalues. So we cannot allow here the non-simple eigenvalues. You can allow, so later you can see that you can allow multiplicity, but only as kept as a finite number. So we cannot allow that there are infinite many multiplicity. So for here, it just makes things simple that every eigenvalue is simple and there's a small gap in between for any n and a fixed s. If that is true, then we have the following theorem, which is an ugly one, but it tells you that the moment problem really has a solution. If the following very complicated sum satisfied. Here, the capital M, these K1 and they're just constants. The K0, they're constants. The mu is the eigenvalues, and this beta is basically the order over dimension for the underlying operator, and Mn is the moment coefficient. So basically, it shows that if the moment coefficient satisfies this inequality, then you won't have a trouble to find out the solution mu. But if you ask if it is not true, can we find? We don't know. Okay, we don't know. This is truly complicated. If you go to another go to the outside this region, it's very complicated. And here just a remark saying, okay, beta basically is the order over dimension. So when the order is greater than dimension, this is true. And okay, so to interpret this theorem in a more human way, okay, then here is the following. If the particular solution's initial condition says the following, so you expand the particular solution's initial condition in terms of an eigenfunction. And the coefficient is not behaving very wildly. It's not going to zero too fast, basically. It's not going too fast. It can be fast, but not faster than this exponential rate. And this alpha is a number between 0 and beta. Then this weighted function exists. And the norm of this weight will grow rapidly when the delay tau goes to 0. So if so basically that's very understandable, because in that case you really can represent anything.
Sorry.
Yeah, sorry.
Does the weight function mu only exist in L2 space? I mean, if there is a possibility for the mu existed in an even larger space,
You can. You hope. Yeah, it's possible here we use L2 basically because that you span the eigenfunctions that's automatically fit into L2, right? So that's the reason here. You can make things work in LP space much more complicated. Okay, much more complicated. And another benefit in L2 is that the computable is very trackable. You just you just need the first frequencies, then you probably get very nice results. And here is a remark that in terms of multiplicity, if you will need the number of initial condition you will need that is equal to the maximum multiplicity, you will get the similar results by very little modification of the proof. So okay, then it becomes a problem. Okay, if the initial condition exists here, then we don't need many other solutions, right? This solution suffices for all cases. How do we find this initial condition? We need the coefficient to satisfy the following relation, this decay relation. And the problem is that in order to select this coefficient, you need to know what is the operator. If you do not know the operator, it's hard to select this coefficient, right? Basically, if you do not know the eigenfunction, how do you select this initial condition? You will have the chicken and egg problem. If you don't know this one, you cannot do that one. If you do not have the initial condition, how do you know you can represent all other solution? Then you will get this dilemma. It cannot proceed. So can we find a universal one? This is a very hard question here. So we don't try to answer that. We just give you some hope here. So the very intuitive choice is that you choose delta function, which has a very similar form that is basically the summation of the eigenfunctions in this very simple form. And if the eigenfunctions are complete, right? Then you basically we want to sample delta functions in the space and see if there's a positive probability that we can get the initial condition that is good, then we're done. So we need this intersection of all the bad sets, intersection of all the good sets. You intersect it together. You need that to have a positive measure. If that has a positive measure, then you're done. There's a positive possibility. You sample delta function, you get your desired condition. And it turns out this actually is very complicated if you look at very general operator. But for this operator, the divergence form, second order, on torus, then using the very ingenious theorem by the Noganov in 2018, and you just use this theorem and plug in the set that is in this form into that, you will show that as long as your alpha is between beta and half beta, this is always true. So for this operator, if the operator comes from this divergence form, second order, delta functions will give you you have a positive probability to sample delta function, which gives you the nice initial condition that it span all the solutions. And that's the thing. But for general case, we don't know. Okay, so this is some numerical test. So this is the case that we have in 2 dimensions, second order. Here we choose a very ugly domain. Here is 2 to -1/4. Basically, we want to generate this eigenfunction that is unique. And and also they satisfy this condition because of the Liouville theorem. So then you can show that you can see. So we try to use this. We generate this initial condition with this kind of solution. So this is in the center, and we use this solution to learn the eigenfunctions. And for the first 8 eigenfunctions, we try to find out what is the relative, or what is I think here is the absolute error or relative error. I can't remember the detail here, but you can see the error grows really fast, which means that when the dimension and the order they're equal, it violates our assumption. And here we give you a case that is not working. Even this kind of particular solution cannot span all other solutions. Basically, you can barely give you a very nice result for the first few eigenfunctions. And for fourth order, So the order is 4, dimension is 2, then you can see the error grows really mild. The error is so here the error grows, that it still grows because because this running error. Okay, so of course there are many applications in this in terms of this section here. It basically means that if your problem is really low dimension, high order, then one solution really helps you to interpolate solutions. Basically, if you sample one solution really well, you can use that to interpolate any other solution in our case. So this is just one case that we show. We show that in different with a different time delay, that what is the error. So basically, if you have a very nice time delay, the error will be very small. Basically, using the, so here is basically just a very easy application of the previous one. So let's go back to the learning part. So we already know that in certain cases, having more solutions will not work. So having one solution really has this usage here. So how do I learn that? So for constant coefficients, it's actually, this problem is not hard, because if you use Fourier transform on a torus, it makes the problem into some polynomial fitting. So everything now in the frequency domain, the exponent here basically is the polynomial, and all you need to do is find out the coefficient of polynomial. So when you choose 2 time slices, then you compare them. Then you can do this. And the polynomial fitting theorem actually is very natural. Basically, you want your frequency to sit in a very nice way that does not give you a very bad case, which is the algebraic polynomial hypersurface with degree less than n. If you can sample the frequency that well, then you can always do that. So basically, it means that this fitting problem has a solution uniquely. Okay, for linear but variable coefficients, if there's no noise, can we do that? Well, it turns out that the previous result will be very hard to work. However, in probabilistic sense, you still can work in terms of if you randomly generate your initial condition in frequency domain. So you use Fourier modes with a random coefficients Wj and a certain set of Fourier modes as the combinations. As long as you have a lot of them, so this R is greater than this combinatorial number, and this M equals this combinatorial number, which is huge. But if you can really have that huge number of frequencies, then as long as the problem is non-degenerate, the leading coefficient are not non-zero, then the coefficient can be uniquely determined almost surely. So basically, the weights Wj giving you some bad cases is measured there. So this is something that giving you the confidence, but also makes you very desperate because you need a lot of frequencies. It's hard.
So for this one, you just need one initial condition.
You one initial condition, but sufficient many frequencies. It's huge. This one in one dimension is fine. It's basically maybe order square. In 2 dimension, it's not affordable. But this is just a theory. Maybe you can use less, but we don't know. Okay, and the proof actually very simple. Basically, you take a derivative at time 0. If you have the dense data near time 0. So for instance, you can choose the time 0 as another delayed number. It doesn't really matter here. The idea is that after you differentiate the solution as time 0, is equivalent to multiply this operator on this solution. Then you form this matrix, and you show this matrix is almost surely non-singular. So this is the idea. Okay, so the takeaways is that if the initial condition has a lot of content, sufficient many coefficients, and the problem is not degenerated, then you can have a unique identifiability, even for variable coefficients, but very unstable. Like we said in parabolic case, you're supposed to be unstable. But for parabolic case, maybe a little bit better. Okay, the stability issue here is just to try to remind you that the stability, how unstable. So here is the if you choose the background as the constant coefficient unification operator, and you perturb the coefficient with some high frequency information. So you add a perturbation on high frequency and also some higher order maybe. Then you can show that the solution generated from this two operator will be very, the difference will be very small. When Q is large, Q is the frequency in the high frequency. So that gives you the instability. It shows that the problem will be very unstable unless you tell me that the coefficients are very smooth. Otherwise, you can always generate a case that makes the whole process break. Maybe assume the coefficient is constant. Is very nice way. Okay, so let's go back. Let's come to this the computation side. So the purpose. Let me remind you that the purpose of the identification does not need the accurate coefficient, right? We only need to know that what operator is inside what kind of dictionaries dictionary terms is inside the operator. We don't need to know what's the exact number of this coefficient P alpha. Answer that question is too unstable. But answer this question, showing that this the second order term is inside this operator will be more robust than the previous one. So here's the setting. So we try not to restrict ourselves to the linear cases. Here this HK can be the dictionary operator, maybe non-linear. Okay, and the coefficient here we assume this maybe space dependent and time dependent. Here is a it's a dangerous way because this is also gives you non-uniqueness. But we also have some restriction. The solution are observed on local patch in terms of open set in space and time, and the patch size has to resolve all the variation of the coefficient. So that means the coefficient cannot vary rapidly. So basically, that is to show the coefficient can only be treated as something smooth on each patch. Then automatically it does not contain high frequencies. And what we do is that we surrogate the coefficient with a constant, and we just believe that it's constant on each patch. Then what can we say? Can we say that the constant is 0 or not 0? This is what we want to do. So we propose a very general method for this kind of problem. So we want to enforce the consistency. Enforce the consistency on all the patches basically means that on each patch you will have a reconstruction. Patch 1, patch 2, patch 3. On patch 1 you will have some dictionary, you get a reconstruction. Patch 2 you get another set. We require all of them give you the same dictionary. So basically, you don't want the behavioral solution change too much from a patch to patch. So this is a very strong regularization actually. It requires that every patch tells you the same thing. So this is actually the key of this approach. And we also want as few terms as possible. Basically, there is a sparsity assumption. The physical model does not contain too many terms in dictionary, and it makes the problems too unstable. And then we feed the data from the local patch of one single trajectory. And this idea actually is very similar to Rudy's result in 2019 in terms of this consistency. But we deal with that with a different way. So this is the basic algorithm. Basically, you have the local regression error. So basically, on each patch, you compute the L2 error. And you sum up as the total regression error, and you define the group sparsity, which is to enforce the consistency. That is, on each patch, you want on each patch, you do some reconstruction, and you want across all the patches, they're basically relatively the same. And you have we define this kind of group sparsity. And we basically march the sparsity to find out the results by minimizing the very heuristic cost. That is the total regression error plus the sparsity. So you can see we minimize the last error. That is to say, you don't want the sparsity too large. You don't want the error to be large. There is some balance in between as the last error. And to do that, we are marching this sparsity from sparsity 1 to sparsity k. Then we say that if we can, then if we find out the final error has a plateau, then we stop. And the algorithm to solve this L0 minimization, we use this basis pursuit. There's no theory guarantee about that. We just have experiments. But is that all, right? Okay. So, but actually, there's some intuition behind whether or not the constant surrogate is really useful. So actually, we can show that it's really useful under these three conditions. So basically, say if the surrogate coefficient really has only two regimes, non-zero and zero. There's no in-between state. That is, there's epsilon threshold there. We will assume that all the constants are in this way, and also we'll assume that all the terms in the dictionary has this good condition number. That is the infimum of all the dictionary over the maximum of the all dictionary sum together should be positive. So basically, you don't want the dictionary to be linear dependent. Otherwise, you don't have a uniqueness, right? You want something like that. So this number is always greater than zero, but could be very small. So this is the issue. Now we need the coefficient to be changing slowly. The coefficient are changing slowly, so we can really surrogate with constants. Then we show that it's okay to use the constant to do surrogate. So if you minimize the L infinity error instead of the previous L2 error, then you can show that if the coefficient is non-zero, then the surrogate should be also non-zero. As long as the condition number is greater than a certain number, 2 times the Lipschitz constant times the patch size over the threshold. Threshold is something you can determine yourself. L is intrinsic coefficient you cannot change. All you need is to change this patch size. So if the patch size is really small, this actually works. So this just shows that if you have a very small patch size, then the surrogate model does not have a problem. But you have to minimize the error infinity error instead, which is also very complicated. It's also a very complicated problem. Okay, so let's see. Let's see some numerical results. The first one actually is a nice one. So you can see that we use the transport equation. Basically, it's the first order. This is the true solution generated by this kind of solution. We massage this coefficient in a very ugly way, basically to make the solution like this graph has some wiggles. So you get a little bit complicated details. And we have two errors to present. The first error, basically the second graph, shows that what is the identification accuracy. So in terms of whether or not you can find out the first derivative term in your dictionary, and it's basically that the error is computed by the intersection of the true set over the set you found over the union over the set union with the true set. So this is called the Gerard loss. But then you can show that basically when you run many times, the accuracy is almost sure, almost certain, 100% with a little bit off. Different radius of this patch size does not change too much, which is nice. And in terms of coefficient error, so after you find out there's only one term in this PDE, you can try to reconstruct the coefficients. So this is the error. The error is also very small. So it says that, so you can regard the third graph as the follow-up step of the reconstruction. After you find out the true dynamics, then you can search for the coefficient with any algorithm. Okay, now then there's a second experiment I want to show. So in this case, we have two different terms in the true dynamics. One is the U times UX, which is the very classical term if you are familiar with the Brocker's equation, and the U triple X, the triple derivative. Here we just borrow the idea from KDE. So, but this equation is no way to be KDE. Okay, it's just something that we try to generate. And here, this complicated numbers basically try to retune that to make the solution has complicated dynamics. So we try to see that if we can learn that. And it turns out that with this kind of initial condition with many frequencies already, and then we can show that when the radius equals 5, the identification accuracy is around 40%. And when the radius is about 10, then you get the accuracy is relatively like 90% accurate. And when the radius is 15, you get almost 100% reconstruction. And you may, then you may see this kind of contradiction. You can see in this kind of example, when the radius gets larger, your accuracy gets higher. And in the previous theorem, it's very intuitive to say that when the radius is smaller, this kind of condition number will be almost certain equation. This is kind of like a counterintuitive. We should have smaller radius give you better results, and the larger radius give you worse result. Because larger radius, you have more variation of coefficient on that patch size. Then it's unlikely that you use a constant coefficient to surrogate, right? It's very intuitive. But here, this is very, it's counterintuitive. And of course, that when the radius is smaller, you get a larger error because the dynamics is wrong. But for radius is 15, you get the accuracy is better. And this reason is because numerically, all the coefficients, this dictionary are discretized. We're not using something like the pseudo spectrum to represent this derivative. We're using the finite difference to represent the derivative. If you're familiar with finite difference method, higher order derivative, when you do finite difference, it automatically introduces even higher derivative inside. Think about the second derivative. You will automatically introduce the fourth derivative. You are using like the 3-point central difference. If you use 5 points, you introduce six derivative. And the more you introduce, the more you add the higher derivative you are introducing. And if you do not involve any mechanism to eliminate this higher derivative, you definitely will be polluted by this discretization error. That is why when the patch size is only 5 grid, you will have trouble because you will have higher order derivative also being identified. Say for instance, UX this term, you will introduce U triple X here actually. If you use a very simple finite difference, then if your dictionary has U times U triple X derivative, you will identify that. To eliminate that phenomenon, you have to choose a larger patch to get away of this low order derivative. And that kind of problem will be contradicting with this theorem, saying that you cannot have larger patch size. There is a balance in between. Larger patch size give you less possibility to make things work, but smaller patch size definitely make your things go wrong. There is a sweet point in between. You have then this is something that we actually do not know. If you use finite difference to approximate the derivative, but if you use for the pseudo spectrum to approximate the derivative, usually you don't have that problem because the burden derivative burden goes to the test function. If you choose that smooth enough, you don't have any trouble. And that is the work by David Bowles in Colorado. It's called the weekly Cindy for using this kind of idea. Okay, so I'll stop here. So this is the end of talk. Thanks.
Thank you. And I think there's one question from the from Zoom. So it's from Michael. So do you assume proximity to the equilibrium?
I guess it's from the very beginning, right?
Yeah. So I think it's when you talk about the setting of your time-dependent problem.
Yeah. So basically, you can so here actually there's assumption that the solution has to leave for a certain time. If you're familiar with the diffusion, you can if here is not diffusion, you invert the diffusion process, your solution immediately blows up. Basically, the solution cannot live for a very long time. If you think about that case, here we need the solution to live for a certain time and keep a smoothness in that time. And rather than that, we don't need any requirement. You just need the solution to live for a certain time. You can measure. That's it. This is the setting. If the solution immediately blows up, then we don't know. Basically, you cannot measure anything. Right?
Any more questions, audience?
How much information do you need to distinguish between linear and nonlinear? It depends on the order. It depends on the order of the underlying. Basically, if the order is given, then one trajectory is enough. Actually,
But you were talking about linear equation, right?
yeah. So you try to reconstruct the linear, right? You use one single initial condition to try to reconstruct linear, and you failed. It's linear. It's the nonlinear.
Oh, okay. Yeah. No, that's an indicator.
Thanks for the talk. Yeah, maybe a few questions to make sure. The first one is at the very beginning introduced the two typical approaches. One is approximation, the second one identification.
Yeah.
So basically, what you are working on belongs to the second.
The second, yeah, the second.
And the dictionary is just the differential operator.
So in the very last example, we use the dictionary of 1559 terms. Basically, it's the derivative up to fourth derivative product of the derivative terms up to three terms product, and some trigonometry function over also inside, some like u times sine of u, this kind of terms. So it makes we try to make the dictionary sufficiently complicated. Yeah.
The second question, maybe I raise later on. Can you explain a little bit why the high frequency information is tough to obtain but critical to your identification?
Which part?
The high frequency information.
Uh-huh.
Why this one is tough but critical to your identification?
Oh yeah. So basically, if you want to, so okay, here will be easier. Okay. The constant case will be giving you the idea. Okay, so here, if you want to find out, so in constant case, you find out the coefficient for this polynomial, and to find out the leading term of the polynomial, you will need a high frequency to be very high to make that term stand out, right? Can you see that when you have high frequency, the leading term will automatically stand out. If you only stick with the low frequency, all the terms blend together. You need one term that grows much faster than another one to make things stand out, like a power iteration, this kind of thing. You have the leading term. The leading term is always easier in this kind of thing. And the more intrinsic way, intrinsic thing, but theoretically speaking, is basically if the polynomial can be identified, it's fine. But numerically, if you really want to do the construction, you really want the frequency here to be higher in order to make the terms stable, right? If I can stably get the first term, it's fine. Yep.
Peter, it's much allowed to talk.
I have allowed to talk.
Okay. Am I unmuted now?
Yeah, I muted it, yeah.
Yeah. So I don't believe the answer you gave to my question before about linear or nonlinear, because any one trajectory can be a solution of a linear equation of any order. It's
No,
true.
not any order. You have to give me the order.
No, of some order. So first order. If I give you any function, that's a solution to a first order PDE.
The coefficient is only x spatial dependent.
Uh,
Cannot be time dependent. Then you automatically have non-uniqueness.
yeah, okay. I'm still not sure I believe this. So you're saying the time dependency of a single solution is going to,
Yeah.
yeah.
So the reconstruction is in probability sense. That is when the coefficient is variable, we only say that you have almost surely the probability one that do the reconstruction if you sample the frequency. We didn't say that if you choose one particular initial condition, that is definitely work. We don't know. You have to be like so if you just run the sample, is very likely it can do the reconstruction. Even for first order, definitely.
Okay. Okay.
Any more questions from the audience or people on the room? Okay, so if no, let's thank Yimin again. Stop.